Hi, I'm Debbie with Nixene Publishing. I'm here with Adrian Nixon from Yorkshire, England, right, Adrian?
Yep.
All right. Good morning. How are you?
Yeah, good morning, Debbie. I'm very well, thank you very much. Actually, it's good afternoon here.
True. Good afternoon. Good afternoon. Well, we are continuing our series on Adrian on the Spot. And Adrian has very nicely agreed to be able to hear some of the questions that our readers have posed, our viewers have posed on our YouTube channel. But this is a genuine question, and this one is based on the graphic that you did for the Graphene FET Sars COVID-2 detector.
Oh, yeah.
Video 19. Someone wrote in and asked about this V and G in the parentheses and said, I don't understand that part. Can you tell me what that part is about?
That is a really good question because not many people do understand the way these things work. Good, it's a technical question. Excellent.
Yeah.
So this is a field effect transistor. Normally on most electric circuits, you've just got two connections. You get electricity going in one way and then it goes out the other way. So it's, you can think of it a bit like water flowing around the circuit.
Right.
And so you can see at the top, you've got the source and the drain. So you've got current coming in through the source and going out through the drain. And if you pass it through the graphene layer, which is the black layer, so we've got those orange things are supposed to represent gold electrodes, which connect with the graphene. Okay. And the graphene is the black layer. What's happening there is you set this circuit up. Let's ignore everything else that's going on at the minute, but you set the circuit up so you've got a constant current going through the graphene from the source to the drain, right?
Right.
That's good. The profile is controlled, well, the current is dependent on the voltage across the circuit. So you could think of the current as a bit like water flowing through a pipe, and the voltage is a bit like the water pressure, if you get my idea about that. That's roughly what's going on here in an analogy. Now, what happens is that the current doesn't just flow through evenly as you change the voltage. So if you start off with a voltage down at one end and you gradually increase and increase and increase, what happens is that the current flow will decrease down to a point and then it goes back up again. It's very sensitive on that profile to, the current's very sensitive to the voltage. With me so far?
Yes.
Fine, right. So you set the whole thing up so that you've got a very carefully balanced current. Now, yeah, carefully balanced current and voltage. Now the gate voltage here, and the VG just means the voltage on the gate. That's another connection which goes through all those insulating layers. This is what makes it a transistor. By altering the voltage on that gate, you can change the way that the current flows through the graphene. So you've got the ability to control the voltage from that gate bit, in effect. And that's the fine-tuning dial you can use on that connection there. Now, the other thing that's going on here is that's all fine and dandy. You set that whole circuit up so it's stable and you know exactly what current's flowing. And usually you'll set it up so no current flows. And because it's like a V-shaped profile, it doesn't have to move very far before you get a big jump in the current one way or t'other. Using that gate voltage, you control the current flowing across the graphene. Now, the way the sensor works is you stick on little chemical groups which have receptors here, which will then bind with and only with the target molecule that you're interested in. And what happens is that the whole circuit is set up with that gate voltage, so it's stable when nothing is attached to it. But if you put a drop of liquid on which contains, let's say, the RNA protein from COVID, then that's on the spike protein there. These receptors here are shaped exactly in the shape of the protein receptors. And so they will only ever bond to protein. They don't bond to anything else. So you can put liquid containing all sorts of other things in and nothing happens because nothing binds to these receptors on the surface. However, when you get spike protein coming in, it bonds to this molecule that's sticking up, and that then sets up a change in the way that the current now flows through the graphene. It's a field effect. And if I'm being honest, I've asked this question of a lot of scientists saying exactly what happens when you get that field effect. And nobody's ever really given me a proper answer to this. But my guess is it's the way that the electricity flows through the molecule at a single molecular level. And so what that means fundamentally, if we scrape everything else aside, that gate voltage at the bottom controls the way that the current flows and keeps it stable. And then when you've got, let's say, our coronavirus spike protein lands on the surface, it activates this molecule, changes the way the current flows, you get a current reading, and that's what gives you detection. That's a very long way around of explaining how it works, but does that sort of make sense?
Yes, it does, and it sounds like because graphene is so electrically conductive that impacts how this works as far as sensitivity, right?
It's not only very electrically conductive, but graphene is very sensitive to what's put on it. So when the electric current flowing through graphene could change with lots of different things, but because it's been functionalized with these molecules on the surface, you're forcing it just to effectively watch out for one particular target molecule. And it ignores everything else. And you fine tune it with that gate voltage. That's what that's for.
Yeah, I was just going to say, so that's what they mean by fine tuning it.
Yeah, and actually, when you dig deeply into it, because you know some of the people I've talked to about this, some really, really smart physicists, when you start digging deep down into what electrons actually are, then it gets very, very murky, and nobody fully understands that properly.
All right, I don't have any more questions for you today, Adrian. We appreciate that. Thank you so much. Thank you to our viewers for taking the time to give us your comments. Thank you so much, Adrian, for your time.
A pleasure, Debbie, and thanks again to the viewers for taking the time to message in. We'll try and do these a little bit more frequently now.